Hey everyone, welcome to Structure Pro. In this video we're going to go over another plane stress analysis example using Mohr's circle. So we're given this setup here, we're asked to find the principal stresses on the element at point H. So we can see we have some kind of a wheel here being pulled on one side, and we're given that the diameter of this shaft is 1 inch. So the first thing we're going to ask ourselves is what types of forces is the cross section of the shaft exposed to where H is. So given that the 400-pound downwards force is 2 inches offset in one direction, 6 inches in the other, we can by inspection say that it's probably exposed to a shear, a moment, and a torque. But we're going to draw it out and just kind of delve into it a bit deeper. I really like these kind of questions because they have a thinking component to them, basically. So, all right, let's draw this out, the section at H, and we'll draw a little red block here symbolizing H. And now let's think about the forces on the cross section. So we have this shear that must be transferred from the end to this point. So I'll draw that in black here. Then we have this moment acting along the cross section due to the 6-inch eccentricity. And I'll draw that in blue. So keep in mind that moment is about the blue dashed line. And then we have this torque. So the torque is clockwise and it's around the shaft's own axis. That's basically what a torque is. It's a moment about a member's own axis running through it. So I'll draw that in green. Next we'll pull out H, the little block, and we'll see the forces on it. So we note, let's start with the shear. We note that it would be acting on the front face, but for equilibrium, we would need an equal shear force acting on the top face. Now remember, this is a free surface, so there can't be any shear on the top face. So we conclude that there's no shear acting at all on block H, because equilibrium states that it can't happen. In reality, the shear force is more carried by the center of this shaft, and it's not at all carried by the outsides because of this free surface. The effect of our moment is to produce a normal stress in the tensile direction at the top of the shaft and in the compressive direction at the bottom because of the sense of this 400-pound force. Similarly, the torque will produce a shear stress on the front face of the element, and this is balanced by a shear stress on the side of the element. Now we can go ahead with some calculations here. So we'll use the formula of normal stress is mc over I, and we'll just plug in our different values. Our moment is 400 pounds times a distance of 6 inches. The c is 0.5 inches from the center, so half the diameter. And the moment of inertia is this formula, quarter pi times the radius to the 4, and we get 24.45 ksi. Then for the torque, tau is Tc over J, so an analogous formula. 400 pounds, this time an arm of 2 inches. Again, this C is 0.5 inches. And J is twice I for a circular cross section, or half pi r to the 4. And we get 4.07 ksi shear stress. Now let's take the time here to convert what we had in the 3D to a 2D, what we're more familiar with, this plane stress view. In this case, it's kind of like looking at it from a bird's eye view. So we have the normal stress and we have the shear stresses on each edge. Now we can plug in our formulas for plane stress. So sigma average, which is sigma y plus sigma x, we only really have a sigma y, 24.45 over 2 or 12.23 ksi. Similarly, we can get the radius of our Mohr circle, or r, using this formula that involves shear stress. 12.23 squared plus 4.07 squared, all square rooted. Remember from the circle that it's Pythagorean theorem, and we get 12.88 ksi. So let's transfer this and view it on the Mohr circle. Give a little bit of context to these numbers. Okay, so I've done a bit of background work here. Now you can see the circle in all of its glory, and we don't totally understand why it's a circle and everything, but it works, so we use it, and it looks nice, especially with these red and green Christmas colors. So take a pause if you need to and just examine some of these numbers, and more of them will come out as we do our calculations for the normal stresses. So I've written down our sigma average and our R at the top, so we can just move ahead and calculate sigma max, for example. This is what we're asked for in the end, sigma max and sigma min, our principal stresses. So sigma max is sigma average plus R, or we're moving from the center of the circle out to sigma max. So 12.23 plus 12.88, 25.1 KSI. So at the point where you have your principal stresses in that orientation, we know that the shear stresses go to 0, which is why, and I'm underlining that here in red, the 25.1 is accompanied by a 0 in the shear stress coordinate. Next, let's do sigma min. So that's just the average minus R. We're moving from the center of the circle to the left, and we wind up with negative 0.65 KSI. I'm underlining that there. Again, the shear stress associated with that state is 0. Take a look at these values I've circled in blue. So these correspond to our initial orientation. Recall how we had a normal force of 24.15 on one face and 0 on the other face, with a 4.07 shear stress on both faces. And we can draw a line across our principal state, which is always this horizontal line. I've drawn that in red. And lastly, we're not asked for this, but we can find it, so we'll do it. Tau max is equal to R, or 12.88 KSI. So that's the maximum shear stress on the element. Okay, great work. Thanks for watching. Post some comments below, likes, whatever. Show some love if you want. If not, that's cool too. And we'll see you later.